travel of molecules, picoseconds is a good thing. And then nanoseconds is something which is much longer in the time. And then microseconds, milliseconds, much longer as well. Okay. Now, if the molecules visit each other every picosecond, that is picoseconds 10 to the minus 12, right? So that is 10 to the 12th times per second. So if the molecules visit each other 10 to the 12th times per second, what then do you guess is the A in our Arrhenius equation that we talked about? Yes, 10 to the 12th. So the A factor, the pre-exponential factor, looking at the Arrhenius equation, which tells us, okay, if I want a reaction to occur, the molecules need to have enough energy to overcome the activation energy. That is given here by delta E, the activation energy, over kT, and then e to the power of minus of that, times how often do they try? How often they try? The 10th frequency pre-exponential factor, Arrhenius factor, is on the order of 10 to the 12th, or at least thereabouts. Sometimes it's 10 to the 10s, sometimes it's 10 to the 13s, but thereabouts usually we find Arrhenius equations. Now, that is not always the case. If we're not working at room temperature, if the reaction proceeds at much lower temperature, then you can also have much slower, much smaller Arrhenius factors. Molecules are slower. So some of my research, for instance, looked at the motion of molecules at surfaces, and there we found Arrhenius factors which were only like a million or so. But then we looked at those processes at a few Kelvin in temperature. And so the molecules are much slower, and so the A values. But by and large, where relevant chemistry happens, the Arrhenius factors are between 10 to the 10s and 10 to the 13s. And then the activation energies. Now the Arrhenius equation is something really important because it gives you the K. It gives you the rate constant for your reaction. And with the rate constant of the reaction, you can then calculate many things about the reaction. The A value, as a consequence, needs to break the units, because the exponential over here has no units, and you know that the rate constant K for different type of reactions have different units, so the A also needs to break the units into the whole thing. If you do experiments, then how you find those values in the Arrhenius equation is by making an Arrhenius plot. You could, of course, plot on the x-axis the temperature and the rate constant on the y-axis, which is shown over here, and that it's an exponential dependence, correct? It looks like an exponent over here, so it looks like an e function, kind of exposed. But that is hard to then, from the shape of the curve, to guess what is the A value, what is the pre-exponential factor, and what is the barrier. So it's really mandatory. Everybody plots those kinds of things in an Arrhenius plot. Yes, you could fit with a computer to the Arrhenius equation, but really what people do is make an Arrhenius plot. And in an Arrhenius plot, you put on the x-axis 1 over the temperature, meaning hot is here, cold is there. And on the y-axis, you put the rate constant as a logarithm. So here it's shown as a logarithm of the rate constant. Very frequently people rather take a logarithmic axis over here and plot the rate constant on the logarithmic axis. It doesn't make a difference. But what you then find is that if I were to take the logarithm out of the whole thing over here and have log k is log a, or ln a, depending on what you're taking, and then times something is ln a plus ln of e. Ln of e is, so it's really ln plus minus delta E over KT. 1 over KT is the x-axis, so they have then a linear equation in 1 over T, the linear equation in 1 over T, where at 0 you have the intercept of the A value and the intercept of the graph with the y-axis. So you could right away read from this graph over here, that intersection is about at 13 and 13. So the exponential factor has to be 10 to the 13. Yeah, because it's wrong. So 13 means it's 10 to the 13. And then the slope going down, the slope over here is the negative slope, this negative sign, and then delta E in units of K. So the slope then directly tells us what is the activation energy. So we just need to put a ruler to this graph over here, measure what is the slope, and we know what is the activation energy of this reaction. How much energy does it cost to bring the molecules close enough to each other so that they can undergo the reaction? And you can read it directly from the Green's plot. It's hard to read it from a plot of the K value of the. So for that reason, everybody uses the Green's. We publish papers, even in good journals like Science, with the Green's plot. So people use the Green's. Okay, but now let's take a step back. Why are we doing kinetics? What can kinetics really tell us? It doesn't, thermodynamics tell us already everything and anything we need. Thermodynamics tells us certainly where is the equilibrium. If I mix red with yellow in order to get blue out of that one, then we have the chemical equation. The chemical equation tells us maybe we make out of one red and one yellow, 2 blues. And then thermodynamics can give us an equilibrium condition and show us right away where is the sum over mu I equals 0, where is the equilibrium, how much of chemical potential, and as a consequence, how much of concentration I need of red and yellow and blue in order so that that is an equilibrium. That's great. So why do we need kinetics? Kinetics we need in order to figure out how fast we get to that equilibrium. Kinetics generally does not tell us where is that equilibrium. Thermodynamics does. But kinetics tells us when will we reach that equilibrium, or how close to that equilibrium will we be after a certain time span. And that can be a slow time span, and so is relevant. Or it can be a fast time span, and might also be relevant. So if you have this reaction of red and yellow making blue, then it might be that even if I waited a year, only an incomplete reaction has happened, and we are still far away from the equilibrium. Now, for a classroom like this, it might be okay, but once you graduate and work at a company which might want to make blue, then that might not be okay if you're making blue that slow. You want to make blue fast, and so you want to understand what factors are involved in making that reaction faster, or making that reaction slower, and so you need to understand kinetics. Okay. You know that kind of thing. Many of you are writing on paper in front of you. I gave some handouts today on paper again. If I were to look at the equilibrium of oxygen in the air and cellulose in the paper in front of you, the equilibrium would be very much on the side of making carbon dioxide and water, and very little, practically none, cellulose being left. But it's not worth waiting for it. It's not worth waiting for the paper in front of you evaporating in front of you into carbon dioxide and water. because it's a very slow process. Now, can you speed up that process? Sure, you can speed up that process. We've seen that over here. Speed up the process, get the rate constant up, just increase the temperature. Put a match to it, higher temperature, the cellulose will convert very quickly into CO2 and water. But at room temperature, it doesn't. And you can see that even small increases in temperature, comparatively small, after all, this is 300 Kelvin, and then this one here is 330 Kelvin, so maybe just a 10% difference in temperature, make an enormous impact on the rate constant, and so an enormous impact on how fast does the reaction proceed. The match makes, it's not something magic, it's just getting higher temperatures, and at higher temperatures you will be able to perform the reaction faster. Okay. But in order to understand these things, I'll copy and paste the slides which I'm usually using Chem 1 for that. Let's look at two molecules of dinitrogen nitrogen pentoxide, N2O5, which is a gas, and which can decompose into four molecules of NO2, which are a gas, and one molecule of O2. So in this decomposition reaction, we can say how fast is the reaction by defining the rate of that reaction. And the rate is increase in molar concentration of the product of the reaction per unit time. So we can of course also say rate is rather the decrease of the concentration of the N2O5 per unit time. So there are actually many rates associated with that reaction. We can talk about the rate of formation of oxygen here. That is then the change of the concentration of oxygen per unit time. And then if I'm plotting the concentration of oxygen as a function of time, then from that plot, I can always look what is the slope of that plot, and that gives me the rate of the formation of oxygen. And I can look at the slope like mathematically taking the first derivative, or I can look at the slope practically measuring over a certain time span how much change in the concentration of oxygen. I will not get exactly the same numbers from the two, but you can imagine how the first derivative is a good approximation to what I try to measure experimentally by taking a certain amount of time, and then over the time I'm seeing how much it changes. And you find that if you look at different times of this reaction, here in the beginning, the slope is really steep. We have a lot of oxygen being produced. And if I go up there, if I'm up here, the slope is much shallower, and I have very little oxygen being produced in the same amount of time. So over the course of the reaction, the rate can change. But I could also look at the rate of decomposition for N2O5. And that is the change of the concentration of N2O5 per unit time. But it's a decomposition reaction, so N2O5 is consumed. So the change over here is a negative number. So the result would be something negative. But people don't like talking about negative numbers, and as a consequence, they define the rate of decomposition, as opposed to the rate of formation, as minus the change of the concentration. This minus sign cancels the minus sign which we have in here for the change of the concentration, which is a negative number, it's going away, and the result will be something positive. Now, what we'll find is that the rate of decomposition of N2O5 and the rate of formation of O2 is not the same number, even if we take into account this minus sign over here. Because for our overall reaction, which we have here, we need 2 molecules of N2O5 to make 1 molecule of O2. So it is convenient to define one more rate for that, and that is the rate of the reaction, not the rate of the formation, not the rate of the decomposition, but something which describes how did I write my reaction. And here I wrote my reaction, and I'll just take the stoichiometric coefficients which I find in this reaction and always put them in front of those changes. Here the stoichiometric coefficient is -2. It's being consumed after all, so it's minus the stoichiometric coefficient and there 2, so it's -2. So I have 1 over -2 over here. Here the stoichiometric coefficient is 4, so it's 1 over 4, it's plus 4 is being produced. Here the stoichiometric coefficient is 1 in front of O, so it's, and it's positive, it's being produced, so I have 1 over 1 here, just like that. So now we have another complication. If people do thermodynamics or statistical mechanics, they always assume stoichiometric coefficients of reactants are negative values, and stoichiometric coefficients of products are positive values. If people do kinetics, they often forget that. And so people then say, okay, this is a positive number by stoichiometric coefficient in kinetics, often defined here as a positive number, even though this is being consumed, and then you need an extra negative sign over here. You always need to look out for what convention is being used in whatever context you're working with to figure out whether the negative sign needs to be there or not. So don't make those mistakes yourself. There's a lot of kind of keeping things in mind. But that is probably good exercise because the other problem is that the rate of the reaction is determined by how I write my reaction. If I gave you the picture of the molecule, what happens in such a reaction, probably half of you would have written this reaction as N2O5 decomposes into 2 NO2 and 1/2 O2 molecules. And that is just fine to write it like that. The problem is the rate of that reaction then is twice as fast. So the reaction rate, the rate of this reaction is defined based on how you write your equation. If you write it in any other way, you get a different rate of your reaction. So you always need to be crucially aware what is the context in which you write about reactions. Because otherwise, your calculations make no sense. They always refer to a particular way of writing that reaction. Okay, and then there's the rate of the reaction given here, where you always divide by the stoichiometric coefficients and take appropriately care of the negative side. Then there's a rate of the consumption, where there's no stoichiometric coefficient in front of it, and where there's a minus sign so that the whole thing will be positive. And there's a rate of production, again, no stoichiometric coefficient. Here we are not interested in how many turnovers of that reaction are there, but just how much C is being produced, and then that is defined this way. So between the rate of the reaction and the rate of the production, there is this 1 over C factor which differs between them, and for the rate of consumption, there's a minus 1 over A factor which is different to the rate of the reaction. Don't stumble over those things. In order to understand how reactions proceed and which ones are fast and which ones aren't fast, it is important to define molecularity. And again, here's the Chem one. You had that all, I know it's boring. Unimolecular would mean at the elementary reaction step, at the fundamental way the reaction proceeds, it's really only one molecule which converts or decomposes into more than one molecule. If I have a bimolecular reaction step, then two molecules need to hit each other in order for the reaction to proceed. That is still, these are the common reactions. Is there something like a or trimolecular reaction? Now it can happen. It can happen. But it's exceedingly rare already, termolecular reactions. Because one molecule and another molecule and a third one all hitting each other at the same time, not very likely. So, and then beyond that, well, maybe impossible. So, if I think about molecularity, the relevant molecularities are unimolecular and bimolecular, and depending on the context, maybe or trimolecular, but nothing more. Let's think about the unimolecular reaction. This unimolecular reaction here might be how the double bond moves from the outside to the center of butenes. So if I have such a reaction, only one molecule is involved, only one reaction is involved, only one product is involved. What happened over here is just that the hydrogen atom moves with the double bond. So if I have such a reaction over here, it depends only on how much of my reactant do I have available, one butene in this case. Earlier, we talked about what do molecules know, and we came to the conclusion molecules know mass, they have their mass. Molecules know velocity, they have the velocity. And from the mass and the velocity, we can calculate the momentum and we can calculate the kinetic energy. So arguably they know them as well. But that is all molecules know. Molecules don't know time. Molecules don't age. Molecules don't wear watches. So they don't know which point in time they are. A molecule cannot say, oh, I live already for X million years or X million microseconds. Molecules don't know about it. The context of time as we know it comes from entropy, and an individual molecule does not know it. So, if I have a unimolecular reaction, then at every instance, the probability for a molecule to decompose into the product is the same. It does not know how long it lived already, and so it cannot depend on how old is the molecule and will it fall apart. It might be relevant for your car, but it's not relevant for a molecule. The molecule does not know time, and so it does not know whether it's due to decompose now or not. For molecules only, in every second I have so much probability to decompose, and it will stay the same over time, that probability. So, if now I imagine for this reaction, the probability is such that after 1 minute, half of the molecules will decompose. Then, if I'm looking at time, if I'm looking here at the time, then at time 0, I have of my molecules A, which should be the blue ones over here, I have 16 of air. I have 16 of the A molecules. And then I wait until the time of 1 minute. Now if I wait until the time of 1 minute, how many molecules will have decomposed? If 1 minute is the half-life time of those molecules, if they have, each molecule has a 50% chance to decompose within a minute, then half of them will have decomposed. So it is minus 8, correct? So how many molecules are left? Now that is clearly those molecules minus class section. Okay. Now, if those ones here, how many will decompose now between 1 minute and 2 minutes? Between 1 minute and 2 minutes, it's again 1/2 of those, correct? Half of those ones which are left, half of my molecules A will decompose. So this is really this one here divided by 2, 1/2 times that. Okay. And they are decomposing, so it is a negative value. So then 4 will be left over here, and then of those 4 molecules, what will happen? Half of them will decompose, and then I can go on. And what I'll see over here, I'll find, okay, it's 2, and then how many will decompose of them is 1, and I can essentially go on. And if I, like this. And if I didn't have molecules, but if I had moles of molecules, then those fractional numbers would actually make sense. But for molecules, of course not. So just by looking at this way, just by looking at every minute half of them will decompose, I can have now a plot for the concentration as a function of time. And it looks like this. It looks like a decaying exponential. It is a decaying exponential. You could make the fit line into this one over here, and make the fit line into this, and the trend line into this, and say it is exponential, and we have a perfect fit, as you can see. And if we look at what comes out of it, then we will find that we started out with 16 molecules, and we have this 0.693 or so for the exponential. So we can right away get some information. But as I mentioned earlier with our Arrhenius plot, sometimes we don't really feel like having exponential plots, because exponential plots are hard to understand. So it's very frequently the case that we rather want to have something linear. So the question is, can we plot something linear? And that can relatively easily be done. And if we are looking at putting on the x-axis, and it doesn't want to do it for whatever reason. Okay. If we put on the x-axis now the concentration of A, and on the y-axis we put delta A, and then we can see that we get a linear dependence out of this, a linear dependence. So the change of the concentration, make it smaller that you can see it, so the change of the concentration as a function of the concentration here is a line. And we can again see, okay, what's our fit function? Let's put that a trend line. Now this is clearly linear, what we have here. Let's put the equation of the plot as well. And there we get 4.5 out of it. So we can get our half-life time back. So y is here the change of the concentration. X is the concentration. And the whole thing is a function like that. So, we only assume over here that over here that we have a unimolecular reaction. We only assumed it's only one molecule which decomposes, a molecule which doesn't bear watch and so doesn't know the time. And we get out of that one that the change of the concentration, and now I'm writing it as the first derivative, the change of the concentration is a negative slope with some factor, we got 1/2 of that, times the concentration of A, because the concentration of A is what we have on the x-axis, right? So we have over here, the x-axis was A, or the concentration of A, and the y-axis is the delta A, or really the slope, something which has to do with the slope, so the A by dt. And it was 1/2 what we got out of it. But 1/2 is a number, so k is a number, k is a positive number, and we got the minus sign. Okay, so from just looking at that, we figured out that the change of the concentration is proportional to the concentration itself. The more reactant we have, the more molecules will convert doing this one. Okay, that is of course an easy differential equation. We can separate the variables. We put the A on this side and the T on that side, so it's 1/A and the dA equals minus k times dt. There, and then we integrate this thing, and we find the logarithm of A in the limits of from whatever concentration we have in the beginning to the concentration we have at a certain time equals minus, and then this one here, k, times just the t as an integral of that, from the starting times p0 to the time where we are really looking at, and then we can put in the limits for that, and we'll find we have the logarithm of the concentration of A minus the logarithm of the concentration we had initially is minus k times t minus our starting time, t0. Okay? We have logarithms, we don't like logarithms, we can get rid of the logarithms by putting it all on exponential. Then we have e to the power of ln concentration of A, and then minus ln concentration the initial, and here we have e to the power of minus k, not the Boltzmann constant, but the rate constant for this equation, t minus t0. Okay, this one over here is the same thing as e to the power of ln of concentration of A. E to the power of minus something is divided by it, e to the power of ln of the concentration from A0, and that is the same. E to the power of ln of something is just concentration of A divided by concentration of A initial is e to the power of minus k t minus t0, and that gives us then as a final result the concentration of A is the concentration of A initially times e to the power of minus k of t minus t0. So we can figure out a rate law. We figured out the rate law from the graph physics Shell showed us. where we realize that the concentration, that the change of the concentration of A is proportional to the concentration of A. And then this was the rate law, a function, a differential equation, which relates the rate of the reaction to the concentrations. And we integrated that, and we then got an integrated rate law over here, which shows the concentration of A as a function of time. This one here was a function about the change of the concentration. This is a function about the concentration. And the fact that that is an exponential decay, that is what we have in Excel as well, because this exponential portion of that we clearly saw in our first graph, in this graph. There we had that it was exponential. There we have it. And 16 was our initial concentration, correct? That is exactly what we should have gotten over there. The K over here doesn't really work out quite as well because my slopes, the way I do this after slopes, were over a certain interval. It was a delta A over delta T, which I used here, not a dA by dt, but we did for precise slopes. So the K is a little bit up. But yeah, okay. So that is what we can learn from that right away. Now, what then would be the case if I said what I'm interested in is this reaction, an equilibrium between the forward and the backward reaction. If I were interested in an equilibrium between the forward and the backward reaction, then I have this equation, correct? I have change of the concentration of A would be how A is decomposing to become B or C or whatever it is. But then as soon as I have some B or C, that B or C, the green ones, they can also decompose themselves and can become back A, like where I put those red arrows in. So, but what I can guess from that right away is that the change of the concentration of A is that there is a minus sign, because it goes away, with the rate constant for the forward reaction times the concentration of A. That was the same thing which we did on the board over there, if that is same unimolecular reaction. And then we have the backward unimolecular reaction, where the rate for the unimolecular reaction backward is the K backward times the concentration of C. And that is making A, so it has a positive sign, because now the change will be positive. So we can immediately figure out this rate equation. So knowing this is a unimolecular reaction, knowing it just goes forward and backward, we can immediately figure out what should be the rate equation. And if I were able to give you homework today, then I would say, do the math, the same math I did on the board over here to solve that. I'm not giving you homework today, I will give you that for homework on Monday, but yeah, that's what we're going to talk about on Monday. Okay, thanks so much.